Hi, welcome to our video solution to problem 7 from Superquiz 2. Here, we're being asked to use Bézout's lemma to prove some statement. Well, maybe it's useful to know what Bézout's lemma is. Well, there's quite a bit that goes into it, but the most common bit, all right, is that, so Bézout's lemma is going to tell you if you have some integers, and let's just take them positive since we can see looking ahead, we're only being asked about positive integers for just simplicity reasons. So if a and b are positive integers, then there exist integers, let's call them say s and t, such that the GCD of a and b can be written as as plus b times t. So there's actually a lot more, as I said, that goes into Bézout's lemma, but for this problem, this is all we're going to need. And we can see here in the statement down below, there is something about the GCD. So that seems like it could be helpful. So let's read the problem. So you have three integers now, a, b, and c, which are all positive integers, in fact. And you know that a divides b times c. So you can multiply a by something and get bc, and such that a and b are relatively prime. So the GCD of a and b is 1, and we want to prove that a divides c. And you can see this is a very natural generalization of Euclid's lemma. So let me just remind you of that. Because the proof here is actually going to be essentially identical to the proof of Euclid's lemma. So that said that if p is prime, and if b and c are integers, such that p divides the product of b and c, then p divides b or p divides c. So if you know that, say, p does not divide b, which would happen, for example, if p and b were relatively prime, then the conclusion would be that p divides c. So that's why this is actually a generalization of Euclid's lemma. So we're going to proceed exactly as we did in our proof of Euclid's lemma. So we can start with applying Bézout's lemma to a and b, and we know the GCD is 1. So by Bézout's lemma, there exist integers s and t such that we can write 1 as a times s plus b times t. Now, ultimately, we want to be able to say something about a dividing c, and there's no c in this picture. Well, there's a real easy way to include a c, which is just multiply everything by c. So multiplying by c, we get c equals, let's write it as ACS plus BCT. Now, our assumption was that A divides BC. And so we do have a BC now, right? There's a BC, which is a multiple of A. So since A divides BC, there exists, let's say, some U in Z, such that AU equals BC. So I can replace BC with AU. And so now each of these sum ends contains an A, so I could factor the A out. And I have A times the quantity CS plus UT is equal to C. Now, everything here came from the integers. C was an integer, S was an integer, U was an integer, T is an integer. And so this sum product is also an integer. And so we have A times some integer is equal to C. Well, that tells you that A divides C. Thus, A divides C. And that's what we wanted to prove.